in downtown Mill Bay. Welcome, Block B and C, who will be doing it for prep. When you're balancing, balance compounds first and elements last. Usually you can balance an element really easily, so if you leave it to last, then you just have to put a number in front of it. Whereas if you balance an element and then you go to the compound, you often have to go back to the element as it changes it. Why are your laptops in? Laptops away. Don't need those things. Unless, of course, you were legally required to.
Wait, did we get handed that on Friday, or?
I would just like.
No, these are your notes from ages and ages and ages ago.
It's that one.
Yeah.
Rather than your booklet.
Balance one compound at a time. Sometimes students, I notice, they're like, oh, I'm doing nitrate, or I'm doing this one, or I'm doing oxygen, or element. And then they notice as soon as they change something, they're going to change something else, and then they panic, and then they're frozen because they know they'll change it. Yeah, do that one, and then go back and do the other one if you need it. If you end up in a endless loop where you balance it, and then something else is unbalanced, and you balance it, and then the other thing that you just balanced is unbalanced, and you balance it, and then you go back to all the other ones, and you go back, start with something else. You started at the wrong point, and you can get into those endless loops if you just start with the wrong element. It's just a guess and try, and if you guess the wrong one, the secret is to erase it all and start with a different one. Only add coefficients. Never change subscripts. H2 plus O2 goes to H2O. You cannot balance things by squishing them together and going, look. If you do that, you've changed it from water to hydrogen peroxide and rocket fuel, and now all the water on the planet is poisonous to us and we're all going to die. They have to stay that way. So we can only balance by doing that. So we're only replacing the coefficients. Hydrogen and oxygen deserve a special mention because they're so often, and they're often combined with so many different things. Put them last if you can. You'll develop an instinct eventually, but just when you're starting out, a lot of times if you leave them till last, it works out a little bit better. Now, someone said it last day. What type of ions are those? Yep. Polyatomic ions. And we're going to do naming next, so we're going to learn about those after reactions. How many of you were here in grade 9 last year in Meta? And I know, oh, excellent. And all of you, as far as I know, loved Meta, and it was the world's best course, and you were petitioning for Meta 10. Sadly, it won't happen this year, but I have heard a rumor they're planning on Meta 11, where they combine 3 courses together. How many of you were excited?
Please no. I'm
I was
terrified.
completely joking. There's no Meta 11, but I do like saying that every once in a while, just to see the reaction. How much naming did you do in Meta 9?
Good, decent.
Like if they asked you to name copper 2 chloride and write the formula, or it gave you FeSCO3 bracket 2, was that a thing you do in a
Yep.
worksheet last year?
Yep.
1 yes, 1 no?
Yeah.
Yes. Okay. Well, if you're worried, I completely redo it, but I want to see if you've seen it. You've seen it though.
Yeah.
No?
I can't really like understand what you're saying. Like when you explain like the
Oh,
in brackets.
if I gave you, could you name that? Oh, not could you? Did you at one point try to name that?
Okay. Yeah.
What about
Oh. Okay.
that sort of thing?
Okay.
Okay.
What about it?
Okay. And always double check after you think you've finished. I started you off doing the teeter-totter method. The teeter-totter method is when you literally try and make essentially a teeter-totter, and you try and make the numbers on each side the same so that it balances out with the idea of the law of conservation of mass, that matter can't be created nor destroyed. It's a method. Once you get good at it, most people just sort of inspect and do it, and they don't necessarily write everything out, but you're welcome to do so. I am going to mention a couple. There's a trick. I think this one has the trick. Yeah, I think it's that one. I'll go here. I'm going to balance it. I've said leave hydrogen to oxygen to last, so we're going to start off with that. So I will balance this, and this has 6. Now, some things in more than one place. I've got oxygen in one place, here in 2 places, but hydrogen's only in one place on each side. That'd be easy to balance. I'm going to do that one next. And once I do that, how many oxygens do I have on that side?
19.
I have 19. I'll let everybody catch up, write it down. I want this to kind of sink in, because this is a trick that will help you immeasurably when you're balancing. Because I've seen students get to this point, they realize they can't do it, and they erase everything. You should never do that. At this point, you can do it. It actually is easier because you left the element until last. 2 times what is 19?
Nothing.
What do you mean nothing?
9.5.
9.5.
Why you copying me, did Oh, I thought you meant integers.
9.5. I do mean integers. Is that correct?
No.
No. Does it balance?
Yeah.
Yes. The rule that you can't have halves is just because chemists don't like halves. It balances, but we're not allowed to do that. What could we do to get rid of the half?
Times
Yep.
2.
Double everything. Just like an algebraic equation, if you do something to one, you have to do it to everything. So the secret is to multiply by denominator. Or in this case, the 2. Now, the next most common thing, hopefully someone will do it. I want to volunteer to deliberately make the mistake I'm expecting you to make, or just give an honest try at answering it. That way you have an out. If you make a mistake, we'll assume you did it deliberately.
For what?
Tell me what all the numbers are.
Oh,
Starting here.
14.
14. What? 14. 14.
12.
12.
19.
19.
2.
Oh, you didn't deliberately make the mistake I was hoping you make. People, as they go through, there's no 1 there. But is there a 1 there?
Yeah.
Yeah, it's invisible. So sometimes people will forget to multiply that by 2, but don't forget to do all of them, even if there's a spot that's blank. 1 times 2 is 2. It's an easy mistake to make. And now it's balanced. All you had to do was use a fraction and then multiply it out and you're fine.
Yeah.
And that's because there are multiple solutions to a balancing problem. I've seen students solve a balancing problem and they get the equivalent of like 6, 57, 36. Oh, thank you. And what's that? 42. And then they go, and then they mark it, minus half a mark, and they're like, why? It's like, well, you could reduce. And if you reduce, then you get the numbers you're supposed to be doing. So you can balance it anyway. You don't tend to get those until later on, and then we throw redox at you because we're mean. You can also balance using algebra. Oh yes, this one. I will demo maybe that one a little bit later, because this is not necessarily for the faint of heart. But if you can balance this one using, you can balance it, guess and check, but it's a little bit more difficult. Notice there's an NO3 here, and there's an NO3 here. Can you treat it as one thing to balance it?
Yeah.
No.
Because it's not in brackets.
You could have, even if it wasn't, if you had HNO3 going to NO3 you could treat this as one thing, and that is 2 things, and then you could go 2 here. But there's another problem.
It's multiplied by.
There's an NO over here that must come from that, so it also breaks apart, so you can't treat it as one thing. So you have to do it just as nitrogen and oxygen, so that trick doesn't work there.
But,
But-
does that other one stay NO3? Like,
Oh, well, that's NO3.
yeah, just the other one.
That one's NO3, but that's NO. And so now you have two nitrogens. The only source of nitrogen on this side is that one. So you can't treat these as, oh, I've got two here, put two here. You've got three nitrogens. So it's a little trickier. It's not a lot. I had students guess and check it, and they've gotten it right. I couldn't the first time, and then I had to use algebra, which is so much more cooler. However, I want you to have a bit more practice with balancing. I'm going to get a demo up and going to introduce the next unit and the reason why we balance. And for this one, now that I told you to put all your computers away, you can bring your computers out. For this, you're going to go to a website. I'm not going to post a key because the website gives you the key for all except I think the last two. And it's just a quick little practice of balancing, particularly if you find it difficult. 4, 5. 1, 2, 3, 4. I'm going to say 4 or 5. You're going to pass along to the back row. So start with balancing. I will get the demo out. It's going to need, well, part of it will need a few minutes.
Wait, where do we get the website?
It's printed on the instruction book. I do apologize. You have to type it all out. But it follows the questions along. You can practice first. And then, or you can just do it and use it to check your answer.
Fun-based. HTML? Did he do it wrong? Wouldn't it be HTML? Wait, I swear it'd be HTML. No. It's HTML. No, but as in like, yeah, I know it says HTML, but is that a real? No, it says on the page it's HTML, but did he make a mistake?
Oh, here. Good question.
Yeah, it says not. Oh, okay, I got it.
How do you get in? What?
Huh? It said it's not safe, but I just said it. No, I just go through.
Yeah, you said no problem. Bro. Bro, I only got one. This one's mine.
No, no.
Yeah, I already run it.
Bro, it said requested URL is not found on the server. Okay.
It's a dot. Yeah.
Sauce it back. Okay.
Sauce it back.
Sauce that.
I just need to look at the title. It's .com/chemistry.
It's fun-based learning. What are you talking about?
Yeah, I know.
.com/.
So you have to find a website, and then it's
Ugh.
basically like
And
calculator
balance.
it does it for you.
But
Except I can't do it, so I don't know what's happening. But it's
Let me
okay
see.
because these are really easy.
Type
anyway.
something wrong, so.
Yeah, it's so free. Yeah, you definitely type something wrong.
How? Wait, what is it on?
Wait, excuse
Fun-based
me.
learning?
No,
I'm sure.
is it HTML?
Yeah,
what do you say, John?
I didn't get
It's
one.
not
Oh my,
like
it's because of HTML.
What?
I changed it to HTML.
I didn't get a worksheet.
What did you change it to and it worked?
Pardon?
What?
Someone just said I changed it to
HTML and it worked. So.
It's supposed to be HTML.
Yeah.
HTM.
Oh,
No?
Yes.
Yes.
HTM sensors?
No, as in.
Oh.
It says
Or
not
is it an
secure.
insurance company?
Yeah, and
Wait,
then just
which
say
site is it?
I don't care. Okay, go to advanced and then say proceed.
Let me try with you.
Oh no, it's working.
Yeah.
It's like it's working for me,
It's
but
like
it says
the connection is not secure.
yeah, go proceed.
Oh, well,
Say
it
advanced and then proceed. Oh, see?
I can use it perfectly.
Yeah, so it's chill.
Yeah.
Doesn't matter if you get
It's
hacked.
still not secure.
for this, you're not putting your banking information.
'Cause you're not.
You should be fine. if you want to be secure, you just put the S in front if you want. Why is my mouse not working? Duh. Not.
Wait, what? How does what?
Oh, yay.
Yo, what's the website with that?
It's on the top of your worksheet.
Yeah, I entered it, but
Okay, I'm gonna try and do what you did. Whoops. Nope.
Yeah, on my info phone.
Type in.
Oh wait, what?
No, bro.
Wait, we can just do the sheet.
yeah,
Yeah.
it's not
Oh,
that hard.
okay.
You can just do it.
Okay.
Funbaselearning.com.
Okay then.
Funbaselearning.com.
Nope. I can't see my mouse. I am particularly annoyed right now.
So Nicole, I didn't get a worksheet.
Oh, someone didn't pass it along. Who's in charge of passing worksheets?
Katie.
You've got one. You've got one. You've got one. How many do you have?
I have one.
You have. Someone here has two. You're going to find out who it is.
Wait, which one do we click on?
What?
Don't click on that, bro.
Wait, there's the last one.
Wait,
Tell me when you
Look at
Yeah,
that.
I shall
Still
tell
sketchy.
you.
just shut up. Tell me which one to click.
You're getting it, bro. This is the website. I dare you.
Is this the right website?
I typed it in and I got that right away.
Nah.
Funbasedlearning.com/chemistry/chembalancer/quest1.htm, so you don't have to click on anything else. It should just come right up. Hands up if you can't get to it.
Oh, it's because I put Funbase. It doesn't. It's not Funbase.
It does not.
There. Anybody else who can't get to it?
So like, what do I do now?
Suspicious.
Oh, okay. What you do is
How do I know?
Take me there anyway. Yeah, yeah, I know. I've evaluated the
You
risks.
don't have
You're
to
good.
use the
yeah,
website.
just do the sheet. You can easily like double check.
Yeah.
There, there,
But then where does
bottom,
it say?
bottom,
Oh.
right there.
Yeah.
I
Why
understand
does
the
it say
risks.
Latin?
No, no, no.
Because
Just trying to be
it's
nerdy.
quirky.
There.
Oh.
Yeah.
Are you trying to access it? Are you sure you want to continue? Yeah, sure. Advance.
You get to 221.
I can't even get on
Proceed.
Are you
There you go.
going to one?
1211.
Don't worry, it's downloading viruses as we speak.
Look,
It's
one
just a
Gaussian,
really old
and that's
website, so it
O2,
doesn't have
O2, and if I just do that,
But
I
as long
have
as you don't type your
H4,
banking
O2,
information
and then
for your balancing,
I
you're fine.
H2, and then
I,
O2.
Mhm.
I entered the whole thing.
Oh, no, you didn't. It's not loading. What do you mean because it's not? Search from you.
Funbasedlearning.com
Yeah, you are tweaking, John.
slash, oh, no, you
Wait,
typed it into
what is it?
Google.
121.
So you searched for it instead of,
Oh.
instead of putting it in the URL.
Yeah, you will.
There you go. Anybody else?
I actually had no idea there was put it in.
There you go.
I did not know that was the thing.
Oh. Wait, for number 8, Zhao, it's just 1111, no?
Yeah, it's already.
Yeah.
Yeah.
Yeah. Yeah. Yeah. Yeah. That sucks.
What do you potential?
432.
Yeah.
it's not 2, I tried for the first one. I mean, for KM and go from there.
4, 2, 4, 1.
I don't know, dude. 2, 8, 7, 2, 5.
The question.
I'm gonna try. You should try do it with an odd number. I'm gonna try. So let's see. 6.
Oh, I already scratched it. Turning on snorkel.
What? What did you get?
I haven't got it.
Oh, Mr. Snow. He was demonstrating a particular explosion, and then it didn't go off when it should have. So they were waiting. He was worried about it, going off, and because now people were coming up, he tipped it on top of it so that when it went off, it'd be completely covered downwards. But that directed so much force at it, it would crack it.
Oh, there you go.
Okay, I'm going to show you the first part of the demo. I have here
4, 2, 4, 5.
in my hot little hand potassium chlorate. Potassium chlorate is KClO4, 3. And KClO3 requires a special use category to use in the province of Canada. It has been banned twice from BC ferries for periods of time, depending on what's going on internationally. You can make gunpowder with it and other types of light or heavy explosives. We actually have to prove that we're not going to do anything nefarious with it before we get to. One of the things it's known for in chemistry labs is a lovely little demonstration in which it will make a gummy bear scream. So I have a gummy bear. I'm going to take the potassium chlorate, pour it in the beaker, put the beaker under the snorkel, and then very carefully squish the gummy bear's head. And as we wait patiently, we realize all of this was a ruse. Nothing is going to happen. We are missing an essential component of this reaction. The essential component we're missing is the topic of our next unit. So in order to do this properly, also, never do this in here to snorkel. We're going to do it in a fume hood. So give me a minute, you can continue working on your worksheet, and I'll put it back in the test tube. It's also, who would do this in a beaker?
Okay, wait.
Now, I will say, it will make a gummy bear scream. Is that an exo or endothermic reaction? Exo. We haven't talked too much about those. That is the next topic. It is an exothermic reaction. The energy is going to come out. But it didn't do it under these conditions. And this is just room temperature, wanting it to go. So we're going to move it and give it slightly different conditions. If you follow me to the to the fume hood where we were last.
That balancing is so light. I know. What'd you get for the last one though?
Huh? Look.
We'll figure it out later.
trees.
How dare you?
How dare you? Think of the trees. Think of the animals.
I got you.
Okay, watermelon is still
Poor animals.
Yep. Okay. In terms of what happened and why the gummy bear burned so well in that, first of all, basically, what is a gummy bear? Sugar. So C6H12O6. I mean, that's glucose. Sucrose, table sugar is like double that, but basically the same thing. We added it to KClO3. This is why it's such a good explosive, is because if you want to react with something, let's say a fire, what is the big problem with making like a campfire and it's going out all the time? What do you do to make it go faster?
More wood.
Oxygen.
Not just more wood. In fact, if you pile a ton of wood on it, it will go out. Over here?
Oxygen.
Oxygen. You can blow on a fire to get it going. If you cut up all the wood, you can provide more oxygen to more places. It's the lack of oxygen that often keeps the fire from going. What this reaction does is it gives off oxygen as one of the steps. And then you get, oops, not that one, KCl. And then the reaction is essentially C6H12O6 plus H2O2 goes to CO2 plus water. And so it becomes a standard combustion reaction. But you don't need oxygen from the air, it's provided in the compound itself. And if it's provided in the compound itself, then that's essentially rocket fuel, that's an explosive, those are all different ways that those reactions can blow up. And you don't have to worry about someone having to blow in the fire in order to get it to go. The gummy bear just goes on its own and it goes until it's completely gone. So one of the reactions here is that is essentially, now I used potassium chlorate. That's the only real difference, but you can keep it as sodium because it doesn't make a difference in terms of the reaction. We get that, it breaks down in a step to give off the oxygen, and then when it's hot enough and it can do that, then that oxygen is all available for this particular reaction. Any soot you see comes from here, and it's because it was burning quite hot and it didn't have enough energy to provide the last little step of oxygen to fully make it all CO2. But that's generally the overall equation. Okay, how many of you are still working on the worksheet?
This one?
The one, yeah, the one I just gave, the balancing.
Oh, okay. I'm still working.
How many are still working on it? Oh, sorry, I'll answer that. How many of you are done? 1, 2, 3. Okay, about half. I'll give you some more time to work on it. I'll go make the lab a little safer, and then we'll start on the next section. Oh, there's the striker. I brought it in. You go shut off the main gas valve.
You hit your hand on one of the things.
Still lost it. Still lost it.
I think Hong Kong might win. Oh, you're going against Lebanon, bro.
Bro,
You
Lebanon's a
expect-
good team, bro.
Really?
The Middle Eastern countries are generally so good.
Yeah, but not Lebanon, bro. Bro, Lebanon's in the middle of a war.
Like
Bro.
Iran.
They don't got time to fund their soccer.
Israel made it to Euros.
Bro, but Israel has money, bro.
That's true.
Lebanon is dirt poor.
Ah, there we go. It's not. Wow. Northern Ireland's pummeling the Bulgaria. Has my king Conor Bradley scored?
Chill out, bro. Stop glazing. Stop glazing, dude. Oh, it doesn't matter. It doesn't matter. I don't think they care.
You can continue working if you need to continue working. If you are done, maybe have a look at this. I'm going to show you how to solve the most difficult balancing with algebra. You start off by assigning it variables like you do in algebra. If this is x, what else must be x? Yeah, those two, they're only one spot. They have to be the same. Any others that are only in one spot on both sides? N. So if this is y, that must be y. Any other relationships that we can say?
N has two places.
No, so n won't work.
N will, wait. Yeah, and then there's H. But then
H.
there's one of these two.
If this is y, what must this be? Y divided by 2. Now that's irritating. So I'm going to say that this is, I was going to change it so we don't have to work with fractions because fractions are evil. We'll make that one 2y. Oh, so whoops.
So that's gonna be
I'll make this one 2y and that one y. That's what I'll do. Are there any other ones that are duplicated on both sides? That like only in one spot? No. There's one spot left. We don't know what it's going to be. So I'll just continue with my XY method and I'll call it Z. If you're American and English is your second language, Z is how you properly say the last letter of the alphabet. But if you prefer to say Z, we'll accept it as we accept any other. Just like when you spell color without the U. Okay, we can now make some formulas. We've already solved for copper, and we've solved for hydrogen, but we could solve for nitrogen. Nitrogen on this side is 2y. What is nitrogen on this side?
X plus
Just x?
X. Oh.
So that 2 would multiply. So 2x plus z. Anything else? No, I don't think so. Okay. What other one was difficult to do? We have nitrogen. What else could we do?
Hydrogen.
Hydrogen, we have a relationship, so we don't need to do that one. Oxygen. So what's oxygen on this side? 6y. And then what would it be here?
6x plus z plus y.
There we go. Nice. Anything else? That's probably good. Now, what we'd like to do is we have a lot of variables in there. It makes it. Can you solve those as they are? No, that makes them kind of hard. So let's reduce the number of variables. An easy one would be this one. I can just say z is equal to 2y minus 2x. Is that good? Anybody feel that was a little weird what I did algebraically? I just moved it to the other side, minus 2x on both sides. Well, if that's true, then I can take this equation and I can go 6y is equal to 6x plus 2y minus 2x plus y. I've just taken z, popped it in, gotten an equation, and then let's just solve that. 6y is equal to 6x plus 2y minus 2x plus y. That's minus y from both sides. Oh, hold it. Y plus y. 2y plus y. That's just 3y. Minus 3y from both sides. And I get 3y is equal to 6x minus 2x is equal to 4x. 3y is equal to 4x. Is that good? It's solved. Can you solve that for what x is right now? Mm. Can you think of a number you could put in for x that would make y a whole number? Like you could use any number you want. 3. So then you do something very clever in math called, let's just make stuff up. And if you make stuff up and you declare it, you're allowed. So you go, let x equals 3. Therefore, 3y is equal to 4 times 3. Y is equal to 4. Good. What's z then? If that is true, then z we already know is equal to 2y minus 2x. Is equal to 2 times 4 minus 2 times 3 is equal to 8 minus 6, which is equal to 2. And then we have x is equal to 3, y is equal to 4, and z is equal to 2. Then you have to go back and pop them all in. So if we went back, x is equal to 3. So we would just go, okay, that's 3 and 3. Y is equal to 4. So 2 times 4 is 8 and 4. And z is equal to 2. Algebra saves the world. And if you balance it out with any hydrogen, oxygen, you'll find it works. Now, could it have worked with any other number if I said let x equal to like 2 or 1 or 7 or anything else? And the answer is yes. It would work whatever number you did. The only problem is that with some numbers you would get a fraction. And then when you're done, you'd have to multiply everything by the denominator to bring it back up, just like we did in here. So at this point, if you can just think and say, what number could I put in where I don't get a fraction? You'll probably hit on the right answer, or a multiple of it, and then you just have to divide. Do you have to know this for Science 10? No, but I just think it's so cool that you can use algebra. Are you doing equations like this in math? Just true. You're not doing this yet?
Yes, we are.
Some of you
You'll
are,
do it later.
apparently. You do it later. Some of you are doing it in different orders, apparently. When you get to this section, tell your teacher, teacher, can we do algebra while balancing equations? No, hopefully they'd say yes. And it also, if you ever hit a problem and you've got time in the test and it's a tough nut to crack in terms of balancing, this method will always work. It's a bit like taking a sledgehammer to crack a walnut. Like, that walnut's going to be cracked. It's probably a lot of effort to go get the sledgehammer, set it all up, and smash it. But when you're done, you know it's going to work. There's the reaction with the screaming gummy bear. We already went over that. And now we're going to do the last little bit of class for 13 minutes, energy and reaction. So you can put your books away, laptops away. Finish it up, whatever you do have left, if you have any left. And we demo I'm gonna do with this, which is why I use the H2 plus O2 all the time. But we're doing a lot this week, so we're probably not gonna do it. Next week I need to ask pretty please permission to use this gym.
I remember when you did that last year while we were in Meta. Like
Yes.
the explosion, right?
Yes, that is, yes. We made Meta exciting for one day. I mean, it's exciting every day. Okay. When we look at reaction, I'm not going to use their gummy bears. I'm going to use H2 plus O2 because it's a little bit simpler. First, balance it. What do I need to put in there? Yeah.
2H2 plus 1 O2 equals 2H2O.
Excellent. When we look at why, now this is an exothermic reaction, as we're going to see next week. A lot of this is already written out for you, but we're going to start with the energy here. We need a certain amount of activation energy. So just like the gummy bear, I had to heat it up to get it going. That's called the activation energy. It's the energy required to start the reaction. But then we had even more energy come out. We didn't just get back the energy down to here. We got, how far, I'm going to go, looks like I went down to here. We got even more energy out than what we put in. The reaction was self-sustaining. So if you light something on fire, you don't have to keep lighting it. It starts to go on its own because that is the activation energy. But this is the exothermic energy that's passed to the environment from here downwards. That is the energy released. Where did that energy come from? Because energy can neither be created nor destroyed either.
Chemical energy?
Yeah, what's chemical energy?
Potential energy?
It is potential energy. Where does it come from? I'm being really obtuse about it because I know people will say it's potential energy, but like what, if you looked at a molecule, where is that energy encapsulated? Bonds. Everything in chemistry is about bonds. So the bonds themselves have individual energies. There's high energy bonds and low energy bonds. These bonds are high energy bonds. And these have low energy bonds.
How do you know?
One of the reasons we know is when we light it, it goes boom, and we get more energy out. So how they literally figure this out is they will react it and just see how much excess energy they come out, and they relate that back to how many molecules did we have in there, how much energy per bond does that make. That means this bond has this much energy compared to, because we don't actually know the absolute number, but we know how much it dropped. So they'll pick a molecule and say, you're 0. Then everything else gets measured against that. Now, what I'm about to write in yellow, you don't have to write down. You can go into Chem 11 or Chem 12. This is called delta H. It's referred to as enthalpy. How many of you have heard of entropy?
I forgot what it is.
No? Did you not watch cartoons? It's like a villain in like half of them. Entropy is, how many of you heard of chaos?
Yeah.
Chaos. I think in My Little Pony season 2, there was the Chaos Dragon, I think. Seasons 1 and 2, by the way, were the best. I think it went downhill after that, after the writer left. But I almost became a bromie, and then I saw the people who were becoming bromies, and then I got scared because they were weird. So, but really like seasons 1 and 2. Pardon? There's a song called Entropy?
Definitely.
From who? Who plays it? That would have been, if it was The Who, that would have been a really interesting back and forth as I was confused. If you find it, send it to me. Entropy is the amount of randomness in the universe, literally chaos. Enthalpy is the amount of heat or energy in the universe. I'm not going to test you on that in Science 10, but you're going to get it so fast in Chem 11 and Chem 12, I feel bad if I leave it out. When it drops, you have negative delta H because the energy came out of the bonds and went into the environment. That's all I'm going to say about it. And that way, if you look back next year when your teacher's like, why don't you know this? You can say, oh, well, he mentioned it. Do products have then more or less energy in their bonds? More or less? If energy came out to the environment and it came from the bonds,
Less.
it has less energy. And the other way you know that is that this is a graph. This is where it started. This is where it ended up. In the beginning of the day, you went to the presentation. How was the Holocaust presentation?
It was good.
Sorry, it seems weird to say that. Like, yeah, it was fun. Like, it obviously shouldn't be fun, but I'm hoping it was good. I heard the speakers were good. I didn't get to go.
Interesting.
Interesting. So with the energy released, products have less energy in the bonds. We have high energy bonds and we have low energy bonds. All of this is a measure of, as someone said, I think it was Alex, and if it wasn't Alex, I'm just going to credit him. So well done. Are versions of potential energy. So the energy in bonds are potential energy. They don't do anything until they come out and get released in other ways. Mitochondria is the
Powerhouse of the cell.
mitochondria is the
Powerhouse of the cell.
that doesn't sound like a whole song about it. Mitochondria is the
Powerhouse of the cell.
we don't even do organelles. I feel like we need to
Wait, are we doing that like in our next unit?
no. You never do it again. Do you
For
do it?
biology.
You might do it. Do you do it in grade 11? We used to, grade 10 used to be like a third of the course was organelles, but now no longer. You take sugar.
She's like mean. She's just mean
You
to a bunch of people.
you take sugar. You react it with oxygen. This is in the mitochondria. You give off CO2 and water, and they'll teach you plus energy. But they don't. That doesn't make any sense. If your cells have little explosions happening, you're just going to rip apart your mitochondria. That's not useful energy. There's no combustion engine in there where you're moving a piston. You have to capture that in a way. So what you end up getting, this does have high energy bonds. These have low energy bonds. And then in biology 11, I think, we cross out the word energy and we put ATP, which is adenoside, and you don't really need to know what it is, triphosphate. And each one of those has a super high energy bond. So if any part of your cell requires energy, it just goes, it gets some ATP and it just breaks off that bond. And so when ATP goes to an enzyme, the bond will literally break off, and that energy will allow the enzyme to swing an arm or move or contract a muscle. You're burning ATP the whole time. It's a chemical. So the mitochondria are the powerhouse of the cell because they make the literal gasoline your entire body runs on. You burn glucose, you burn protein, you burn fat. All of that is to make ATP. If you run out of ATP, you're dead. It's required. That's why zombies don't exist. Zombies are like running around and everything's like rotting off. They're like, where did the energy come from? They don't have ATP. There's no biochemistry there. Doesn't make any sense. Bothers me every time I see the movie. Although now my headcanon is they have energy because nanotechnology. They're being animated by little robots. maybe a self-healing factor from some super advanced alien race or future humans. This is not time at the bottom. And I get irritated when people call it time in Chem 11, so I want to make sure we do it right. Answer those two questions based on what we just said. And I'll ask you random people what they are. This is the time we found.
Kristen,
Mm-hmm.
do you teach science 11 or like Chem 11?
I have taught it. I taught it 2 years ago. I'd once taught like 3 or 4 years ago. I taught 3 sections of it, all 3. But I don't know what I'm teaching until I arrive here in September. This year, I was going to be teaching Science 10, 1 class. I think 2 Chem 11s and a Chem 12. And now I'm teaching 1 Chem 12 and 3 Science 10. And I've never had a year with what they told me I was going to teach was what I ended up teaching. I won for a few years. I taught Math 9.
Math 9.
Yeah, I know, it was surprising to me. But then again, how hard is Math 9, really? I mean, it's hard, but I did make a mistake in it because I was teaching Tyler Van Keeken and he made me make a mistake. And then the tour walked in and that was embarrassing. Okay, what gives off energy? What type of reaction? Exothermic. And then I didn't tell you specifically, I shouldn't write in red on red. However, since that's exothermic, it makes sense if it's red, I'll make the other one blue. What takes in energy? Endothermic.
What's an example of an endothermic?
Can anybody tell me an example? I'm going to show you one where things get, in the same way a reaction can get hot, these can get cold. However, there's very few of them that are self-sustaining. Because this reaction gives off the energy it needs to continue the activation energy so it becomes self-sustaining. Whereas endothermic reactions are drawn a little differently. I'd like you to draw your best guess of what that would look like in pencil. But can anybody think, does anybody know a reaction of an endothermic?
Could it be like a black surface, like the sun?
That's just, I'm sorry, that's just sucking in energy. That's not doing anything with it. But it is taking energy in. Pardon? Yes, but now we have to answer this one question.
Okay, like a kettle boiling water.
Kettle boiling water. No, it's not a chemical reaction, but it is endothermic.
Oh, okay.
Because it requires energy to continuously happen. If you stop supplying the energy, it stops. So all of cooking is endothermic. Okay, you can go. Yeah. I'm going to post the worksheet online. There was going to be a worksheet for this section. I'll have physical copies next day, but I'll probably post that as well if you're looking to get ahead. Today is Monday. On Friday, we will be doing the lab. If you already did the lab, you'll be focusing on part 2. If you haven't done the lab, you'll be focusing on part 1. Pardon? Today's Tuesday. We'll be doing our lab on Thursday because they changed the blocks already. Yes. I keep saying today's Monday. Thursday. Thank you very much. So that is the day after tomorrow, the very next class.
Well, that joke was not it. What? That joke was not it. Have you done